Hmm. Oh, that's weird. There we go. Hmm. Good morning, everyone. Welcome to lesson 10 of Civil Engineering 3372, Water Systems Design. And the topic of today's lesson is a continued exploration of the EPANET computer program. And today we're going to add two new components to our knowledge base, pumps and tanks. So I have on the screen, I should be sharing, what you should see is my browser, and it should have like Atomic Kitty, Lesson Lab, Teaching, Homepage, Jupyter, and so on, tabs at the top. And if that's what you're seeing, things are working as I anticipate them. And I'm not sure if you get to see me talking in a little teeny window in a video, but I assume you will, so I'll try not to do anything embarrassing or drool too much. So first question for me to y'all is, indeed, actually, let me make sure I'm recording this. Yeah, I am, okay. Are you indeed seeing what should be a Blackboard page right now? You can either unmute yourself and say, yeah, I can see it, or you can type it in the chat. Perfect. Thank you, everyone. That's good. That verifies that the one-way communication process is working so that I can talk in your sleep, which is what most professors do. For today, I'm going to need to have my EPANET window open, so I'm going to open it right now. I hope this is still running. I've had very difficult network issues all morning today, which I suppose is kind of the way things are nowadays. Let's try again. Sweet. Okay, that's what I wanted. Let's go back to Blackboard. I just have it there idling now. We'll get to it in a bit. And so the lesson collection, as of right now, does not have the link. This is getting kind of embarrassing, doing this over and over again. Create a folder. Call it Lesson 10. Hit submit. Go into Lesson 10. Create a web link.
Yeah. Okay. Everybody, it's not in the bathroom, although the seat was warm, so we may have just missed it. Yeah. My money's on the table. It's not a fight. How could they do that? I don't agree. Take it back. You just agree with me sometimes. Am I scared of getting hit in the face? No. Every day, weirdos pay dominatrixes hundreds of dollars for that very privilege. I'm scared I'm going to love it. Do this. Okay, guys, I can handle this. But I can go home. We're here for the show, my call. We're just a bunch of players.
Oh, it's just getting fun. Okay, that should get us into Lesson 10, and one thing I'll have to fix. All right, so let's go back and try to do it correctly. So my exercise of profanity in the online teaching world has increased greatly. We will go back to the home page, and now we're cooking with gas. So lesson collection, lesson 10, and the one and only link there should be a link to this web page, which is not currently rendering properly, but I will fix that right before your very eyes. Get the correct style file. Oh, it's just not going to play today. Okay, well, this will be, we'll have to do for the time being. So all those tabs are still functional. And the lesson for today is Tanks and Pumps in EPANET. Has the usual links from Tuesday's lesson and various paths to some interesting things. There's I have a 2018 version of this lesson, so I'll get that put up onto YouTube. And again, I'll put today's up as they are completed. In the supplemental data, we should find a directory called EPANET files, and in it there is one called example 4, example 5.1, and example 5.2. And I'm quickly going to look at the bitmap images. So example 4 will be the pump. Example 5.1 will be a network with a tank or a reservoir. And example 5.2 is pretty much the 5.1 network, and we add a reservoir and a pump and a little bit more pipage. So by the end of today's lesson, you will have seen 6 reasonably relevant examples in EPANET, and then building out from these to more complicated networks is relatively straightforward. So without further delay, let's continue. So the lecture should be Lection 10 PDF, and hopefully it rendered. Well, that's not what I wanted, but that's going to have to work. So pumps in EPANET. So we've done EPANET last meeting as an alternative to writing our own computer programs or attempting to create network simulators in Excel, which is doable. You can do it, but it's not easy. It's difficult to keep track of what's going on. So we will continue with that. We're going to do a simulation without a pump, and then we will look at adding a pump, just a generic pump problem, and then we'll do a simulation with a pump. And so the first one is this. We want to compute the discharge in each pipe and pressure at each junction node for the 8-pipe system that's shown in the picture right there. So the pipes are 1, 2, 3, 4, 5, 6, 7, and then 8 connects the tank into the network. And these little arrows are representing demands at nodes 1, 2, 3, 4, 5, and 6. We're also provided with network information on the pipe identification number, in this case 1 through 8, the length of the pipe in either meters or feet, the diameter of the pipe in either millimeters or inches, and a friction factor. So this particular example is taken from one of the readings, Werbs and James, and back then in their book, the method of solution was a Hardy cross type of approach, in which you entered the friction factor and computed everything. So EPANET doesn't allow us to have the friction factor from the Moody chart as an input item. What we can do instead is we input everything else and it will compute a friction factor. So we can create this model and run it a few times and see if we can get the friction factors to more or less match. Usually it's impossible to get an exact match for this problem or any other problem. And that is a consequence of the knowledge base having changed over a 40-year period. So EPANET uses a type of Jane equation approximation, and at certain input values that are typically encountered, parts of that equation go horizontal, so there's no change in friction factor with change in other features. So getting exact matches is essentially impossible. We should be able to match at least within order of magnitude and possibly within 20 or 30% of these published ones in this example. Continuing with the example, we're also given information on the junction node ID 1 through 6, the elevation of the node in meters or feet, and then the requisite demand at each node, in this case liters per second or gallons per minute. So that would be a fairly classic engineering analysis problem. And our goal would be to analyze this and find the node that has the lowest pressure. And we can't really do that by looking, although we can actually make a pretty effective guess. The lowest pressure node is going to be farthest away from the supply, and it's going to be at the end of larger diameter pipes and probably corresponding with the largest demand. So node 6 has a 1,500 gallons per minute demand. It's roughly the same elevation as the other ones. So I would guess that node 6 or 5, either of these two will be the low pressure nodes, but we'll find that out. So to do that, we could follow the modeling protocol that I presented in our last meeting, which is to sketch the layout on paper, identify pipe diameters, length, and roughness values, identify node demands, node elevations, and node demands, locate the supply reservoir or tank, and identify the pool elevation. And then if there's any pumps, we want to identify those and prepare pump curves in the problem units. So the layout of the sketching and layout is pretty easy. There's the picture right there. And then the pipes are identified in the pipe table corresponding to the sketch. And I have a note here in the presentation. We use 0.26 in the Darcy-Weisbach model, head loss model, as our initial roughness guess, and we'll adjust it until the computed friction factors come close to these. Then we identify the nodes, their elevations and demands, and the last thing we have in this problem is a tank. This is a steady flow problem, and so there's no extended period simulation, so all we really need to supply at the tank is the pool elevation. And that would complete this problem. So let's, I'm going to go over here to the EPANET online representation, and I have to do something else first. I don't have the files here yet. They're not pre-placed, so if I go to my EPANET file thing, and I look at my examples, nothing. So I need to get examples 4, 5.1, and 5.2. So the way I'm going to do that is from here I will connect to my server and grab the files and pull them over. So give me a second to do that. Maybe 2 seconds, maybe 5, maybe 10, 15. Yeah, network does not want to work, does it? Oh, sweet, there we go. Okay, so I'm going to have very long lag times. So today we'll have to be somewhat patient. Oh, you didn't want to close it. All right, with any luck, this one will be, let's see if it's going to work. So I'm going to browse to the server where I have the data stored, and I'm going to get a red warning tab that says, the computer has detected that you have not entered a credit card number yet. I will no longer work. Click Restart to complete the update. Oh, you're just not going to work today, are you? Well, it'll be a short lecture. That'd be good for everybody. Go home and have mint juleps all afternoon. All right. Let's just go in to the front door before we try to get to the server. Three, 1, 3, 1, 4, 3, 2. All right, let's see. Yeah, it's just not going to work today. That's a bit of a problem. Okay, plan B. And it did not copy paste because it's a piece of junk. So I'm trying to get the files here because I don't have a working copy of EPANET on my computer, but I have one at this website. But if I can't get the files there, I'm sort of have a problem. So I'm going to try wget. So it's wget and then the path to the file that you want to get. So wget. And the path is, let's go find it. There we go. All right, so that should that'll get me close. Now I got to go ahead and get the actual file. So the actual file name I want is example 5-1. I really hope this works. You need to accept input. X A M P L E -5-1. And I want to get network 005-1-1-bitmap 005-1-1-net. All right, here goes nothing. We'll find if this actually works. So a wget should be able to go out there and bring it locally. Good, that worked. Okay, so that's how we can get files from our remote to this machine. And let me get the other two that are associated with that. We want the bitmap. And type the name wrong. BMP. Oh, it's network. I did type the name wrong. Damn it. NETWRK 005-1-1.bitmap. -5-1. It wouldn't kill me to get the correct directory. Okay, let's hope that works. Yay! So now check that the two files are there. Indeed they are. Let's go ahead and create a directory form. We'll call it example 4. Actually, I think I'll call it example 5 so I don't confuse myself later on. Shrinkify that. Go here, and now we go to our example directory. There's example 5. All we need to do now is put that into example 5. But instead it's going to go into equal pass, I bet. No, it did it correctly. That's quite unusual, actually. So example 5 has our background image and actually an already built network. Out of laziness and time saving, that's there to speed things up. You wouldn't know I sped anything up given the last 10 minutes. So we'll now run our EPANET model, and we'll start to build that network and address the questions that are asked in the problem statement. So we already are in a new thing, so all we want to do right now is we're going to load in our backdrop, which will serve two purposes. One of them, it'll actually get us pointing to the correct directory for this problem. So there's example 5, there's the bitmap. We'll see if the miracle of computering happened. It did. Okay, so that's our base map. And the other information we need is the pipe lengths and pipe diameters and the node elevations and node diameters. But returning to our modeling protocol briefly, sketch the layout on the paper. Done. In this case, start the program and put the drawing into the program. Done. Identify pipe diameters, lengths, node elevations. Those appear in these two tables. So what we will do is we'll build the network and then we'll refer back to these tables to get the various lengths built in. So to do that, we would start by drawing nodes. And this time I'm not just willy-nilly doing dots, I'm actually doing them in the sequence that the nodes are labeled. So node 1, 2, 3, 4, 5, and 6. And then we will draw in pipes, and I will join pipe 1 from node 2 to node 1, pipe 2 from node 2 to node 3, pipe 3 from node 1 to node 4, pipe 4 from node 2 to node 5, and pipe 5, stop right there. And pipe 5 from node 3 to node 6. Pipe 6, I'll go from node 5 to node 4. So I'm choosing the directions not entirely arbitrarily. I have kind of a preconceived notion of what I think positive flow directions are, and it's just easier to draw it that way. So now the network is created, and we have to create a tank. So there's our tank. Tanks, you're welcome. And then we will join that into the network. Let's turn off the backdrop. And so we've drawn the network. Drawing the network is relatively mind-numbing, but doable. So the next thing you would do is you would systematically go, for example, this is node 1, and it has the correct numbering because of the way I actually picked them ahead of time. We'd want to supply an elevation. To do that, we would go back to our node table and find the elevation of node 1, which is 170 feet, and we'd put 170 in here. We would also go back and put the demand. We have a demand at node 1 of 500 gallons per minute. So we would go ahead and put the 500 gallons per minute. And we do that for all the nodes. And I'm going to cheat at some point. I'm actually going to load in the network file. Then for each pipe, we would repeat pretty much the same activity. We'd go to the pipe and go look at our pipe information. So pipe number 1 is 4,000 feet, 10 inches. So we would go pipe 1 would be 4,000 feet, 10 inches, and we'll use the actual 4,000, which is 10 times longer than 400. And then we would supply a roughness value based on our head loss model. In the notes it says start at 0.26, and we'll adjust from there. So 0.26, and we would repeat that for every single pipe in the network that we want to simulate. We set our project defaults to have the correct model, in this case Darcy Weisbach. And we're good on that. And our flow units are gallons per minute. Alternatively, if we did this in SI, we would probably be using liters per second. And so that would conclude building the model, and then we would run it. So if I run this, it won't run, because right now it's broken. But actually that's worth doing. So we haven't completed data entry, and we get a warning message like that. And it tells us negative pressures. Actually, I'm surprised it even ran that far. But that's usually an indication that we've built something. We've conceptualized our networking correctly. Let me go ahead and just open the existing model. 9. And so there's the model. This one's been parameterized correctly, so we can go look at a particular pipe, and we see length, diameter, roughness in this case is 1, so this must be after some experimentation has occurred. And if we run this simulation, we get the always desirable run with successful response. And we can examine node pressures, because that's something we want to do, and find out that light blue represents low pressure, and so node number 1 is 49, node 2 is 48, node 3 is 40, node 6 is 45. So I was incorrect. Node 3 is the lowest pressure node in this network. If the question was slightly different, what's the lowest head node? We would conclude that the lowest head is node 6, which is what I initially thought would have been the low pressure. In terms of the lengths, we can report the flows if we want in cubic feet per second. We can change the flow units, but I'm not going to do that because let me check the demands. So these are in cubic feet per second right now. So that would be how we would handle that problem. So the next question we want to address is, what if we want to add to this network and put a pump in it? Well, first we're going to learn how to do pumps in a really simple example. So in the modeling protocol, we have the statement, identify pumps, express the pump curve in problem units. So there were none for that problem. Let's look at a different problem. So here's the actual output that we just saw live, and there it is in Memorex. And you can adjust the roughness coefficients to try to match the friction factors to agree with the original table. And here's an example of one instance of that. We also could generate a full status report, and this figure is showing an excerpt from the full status report. If you recall, on Tuesday, we would generate the report here by choosing report in the report tab, and status as the status report, or instead to do a full. So we choose full, and it will save it back to the directory of interest. We can then open that directory. Read the report. There's not much in it. Numbers, letters, pretty much everything you need to make an alphabet. So it tells us the run date, input file name, the version of EPANET we're using, the link node table. So there were 8 links, 8 pipes in the problem. It tells us the starting and ending node IDs of those pipes, how long the pipes are, the diameter, and it has the node information, has the node ID, either the explicitly supplied demand or the computed demand in the case of a tank, the head at each of those locations, the corresponding pressure based on the node elevation, and it identifies our fixed grade node, in this case a tank. And lastly, the link results. It has the flows in the different pipes, the velocities associated with those flows, the head loss per 1,000 feet, and whether the pipe is open. So that's a report. And from a report, you actually can usually reconstruct an entire model. So if you somehow manage to lose everything, but you still have the report file, it's possible to reconstruct the entire model. So we've just seen that in real life. So just as a quick mentioning, the problem was given in gallons per minute, and so the change I made to go to cubic feet per second is absolutely unnecessary, and it's a complication. But it was there when I built the example originally. The velocity coming from the tank into the network is at 15 feet per second, which is roughly 50% higher than anyone would want. We usually don't want to exceed 10 feet per second because that has some certain implications in terms of managing forces when the water has to be turned to the left, right, up, or down. The design guidance, where it is explicitly stated, ranges in the 2 to 10 feet per second range, and your preferences are go on the lower end of that range. So in this case, we would perhaps consider a larger diameter pipe or some sort of flow control valving. So our next conceptual step is, how do we add pumps? Pumps in this computer program are treated as links between two nodes, and to that link we assign a pumping curve property. In the case of putting a pump link in, each of the nodes to which it connects must have appropriate elevations. By appropriate, I mean they can't. You don't want to put goofy elevations in because it'll confuse the heck out of you. The pump itself is added as a link, and then a pump curve is specified for that pump. The program by design will operate the pump out of range. So if the pump curve is insufficient for the pump, the program is designed to pretend that there is adequate pumping available, but it will report a set of warnings to you if you supplied a pump curve that would have to operate out of range. So that's actually kind of handy because it helps you identify in a design pumps that you've specified that are hydraulically inadequate for the conditions that you are inflicting them upon. So we're going to do this this example, which will be the example 4. We'll have to go through that whole get the file thing again, but I think I know how to do it now. So instead of taking 10 minutes, it'll only take 9. So here's our diagram. We have two reservoirs, the lower one and the upper one, and their pool elevations differ by 10 meters. And what we want to do is we want to lift water from the lower reservoir and put it into the upper one. So we want to lift water 10 meters. We're going to use a pump, and we're going to do that through a suction pipe, which is 4 meters long. The pump impeller is located 3 meters above that pool, and then it discharges into a 100-meter long ductile iron pipe. And we're told the pump performance curve is it's 15 minus 0.1 Q squared. Oh, that was a big yawn. Oh, I had the video on too. I feel better now. The added head is in meters of water, and the flow rate is in liters per second. And our goal is to analyze the flow rate in this system. So if we have a pump that follows this performance curve, we put it in this hydraulic system as depicted in the drawing, flip the switch, what kind of flow rates can we expect? So to do that, we would follow our protocol, which would first sketch the situation. So we'll go ahead and put that sketch in EPANET in a second. And then we would construct a network and put the pump in. So sketch the layout on the paper, identify pipe diameters, length, roughness values, identify node elevations and demands, supply reservoir tank, identify reservoir pool elevations, identify pumps, and supply the pump curve and problem units. And that gets old when I say that over and over again. But there is method, because this protocol will give you good guidance in the future when you're doing these models if you don't do them every day. So sketch the layout on the paper. That's the layout we want to use. And this sketch is contains almost everything we need. It has our 2 pools. It's showing a node here which would handle the lift part, and then we connect a pump to a node here, and then we connect that through a pipe to the upper reservoir. And then the pipe lengths are shown here, and the roughness coefficients are shown in this table. So let's move on over to the program. The individual node elevations, the node on the pump is set 3 meters above the pool elevation of the lower reservoir. And then the upper reservoir is goes through the 100-meter pipe to get to it. And then the individual pool elevations are 0 and 10 meters. And that is pretty much all we need to specify the necessary information, except for the pump curve. Sadly, we can't just type an equation into the computer program and have it reflect a pump curve. We have to build the necessary information. So 3 or 4 points is usually sufficient. One of them should always be shut off because it's easy. There's no brains required to specify shut off. Then the next 2 should be at reasonably distributed locations along the pump curve. So 5 liters per second, the total head is 12.5 meters. At 10, it's 5. And that's the information we will supply when we build the pump curve. So we're going to start with this. So here it is in EPANET. So let's go ahead and first get the data files. And I'll do that by creating an example 4 folder. Hit create. Then I will do all my wgetting. Oh, that's really sad. Maybe it's that one. Yes, okay, good, it's still there. Okay, so it's currently empty, but we will just modify this webget. So example-4 is the housing directory. And we need to get the P2-39 BMP is the picture. P2-39.bmp. Let's hope that's correct. Sweet, we got it. And while we're there, we'll go ahead and I'll grab the folder, the file that has the network 2-39net. And everything's in the directory as we wanted it to be. Close that. And we will create a new program. Open a backdrop, which will get us into the correct directory. And there's our drawing. And then we want to go ahead and create the model. So as before, we would want to first set the program defaults and then create the necessary nodes and links. I'm going to cheat, and I will go ahead and just open the existing network, which is already built. And this will help us illustrate the model. So in this case, we're using straight connections and come on. So there's our model. And if you care about that curved line, you can go into the effort to add vertices and make that pipe visibly render as curved, although it's still just a 100-meter long pipe. So let's look at the different parts of it. So pipe 2 is 100 meters long, 100 millimeters in diameter, which is from the problem statement. Initial roughness 0.26. This upper reservoir, known as reservoir non-responsive, is set at a total head of 10 meters. The lower reservoir, also non-responsive, is 0 meters. This junction, which connects the suction pipe to the inlet of the pump, the junction is at elevation 3. But the pipe that connects to the junction is 4 meters long. So that means the pipe is drawing water from one meter beneath the surface, which makes sense because then it will suck water instead of air. So we've done the two pipes. Now let's look at the pump itself. So the pump is somewhat tricky. So it has a pump ID. So its ID is 3. And it's going to use pump curve number 1. So the way we would enter pump curves is we go here into the data window in this browser and we choose curves. It's very confusing because you see the word pumps and one would logically think that a pump would be where I'd enter pump curve, but that's not correct. We go into curves, we have curve number 1, and it tells us what the curve type is. It's a pump curve. Its ID number is 1. We can call it anything we want. So I'll call it my cat Mercy, the one who just meowed in the background. So it's the Mercy pump, and we choose OK. And here's where we entered the pump curve information. So we put the flow rate in the added head, the different flow rate in that added head, and the flow rate at 10 meters per second, and that added head. You'll notice it tries to provide an equation. And in this case, the equation it provided is an exact replica of the equation we wanted to use. But that won't always be the case. So if I put like an 11 and 4, it can't fit the equation, although it can still render, it can approximate a pump curve. So once we go beyond the 3-point curve, it's not well suited to estimating an equation. So let's return back to the original setup, choose the okie dokie function. And now when we go back to the pump, we have to identify which pump curve we want to use, and we want to use pump curve named Mercy. And now when we run the simulation, it's going to attempt to lift water up here, and I think the answer is around 6 liters per second. So we run it, our run was successful, and we can get the flow lengths. Currently it's not reporting results because we told it we didn't tell it to. So we can go into options, notation, and it's reporting 6.37 liters per second of flow is running through the pump. On the suction side of the pump, we have a slightly negative pressure. On the discharge side, we have a positive pressure of 10 meters. What's up, Mercy? You gonna teach the class? I bet you do a better job than me. So that is how a pump is entered. And so the key features are a pump connects from an inlet node to a discharge node, and then that connects throughout the network. So we'll take advantage of that in the next example. So we've essentially done this problem right there, live right before your very eyes. So now let's return to the network case, and now we're going to do the example where we have a pump. So the problem statement is we're going to take the prior network and we're going to add a few more parts to it. So we would sketch layout on paper, identify pipe diameters, node elevations, demands, reservoir, pool elevations, pumps, and pump curves. So here's our next network. The portion that's colored in light blue, we've already built a simulator for that. That was our example 5, or what I call 5-1. We can now try to do a second example, 5-2, and all we'll do is we'll just add this additional parts of the network. We'll put this reservoir here, and we'll put a pump here. The added information would be these additional pipes, pipes 9 through 14, with their respective lengths in either meters or feet, and their respective diameters in either millimeters or inches. And again, if we're doing it the oldest way, we would actually supply explicit friction factors. In the EPANET case, we'll supply material properties, and it computes the friction factor. And then at the new nodes 7, 8, and 9, we have specified elevations and specified demands. And then we have to put the pump in, and we're given pump curves in this table here. So what this table is showing, this column labeled E sub P is the added head or added energy that the pump supplies. So in terms of feet, for instance, the pump adds 200 feet a head at shut-off, 175 feet a head at 10 cubic feet per second, 110 feet of head at 20 cubic feet per second. So we need to have that information prior to starting to build the model, or we will get a little bit locked up when we're building the model. So this is the model we'll build, but we'll go do that live shortly. And I'm actually going to load the completed network file and the picture in, and then we'll just explore the parts of the file. The key thing here is in this particular example, the person that built the model used the reservoir as the inlet node, and then put the pump between that node and node number 9. I think in retrospect, a smarter way to have done that would have been to put an additional node here, so the reservoir goes to a node, node goes to a pump, pump goes to a node. The end result wouldn't be different, but it makes more hydraulic sense to me that would have been the way to do it. And then here's a status report. So let's go ahead and we'll look at this model. But first, I want to get the names of it. 5-2-1. Got it. So I'm now going to change to the example 5 directory, if it'll let me. And we want to get the 2 files. So it's example 5-2 exercise 005-2-1. Oh, it's got an input file. We'll actually do the input file because I don't often show that. So get the name, exercise 005-2-1. So those come almost instantaneously because they're actually quite small in the whole scheme of files. And we need network 005-2-1. And ta-da, it's here. And so we'll shrink that. We can open it in a second, but I want to show you what the input file looks like. That's a little different than I've shown you before. So here's this file called .inp. If we open that, it's just an ASCII text file. And it has the network built in the input file format. So it's got the junctions identified, reservoirs, tanks, you're welcome, pipes, the pump, and it tells us what pump curve to use. And if we move down here to curves, there's a curve right there. The curve name is 1, and it has the pump performance value of 0, 10, 20, 200, 175, 110, exactly from the table. So these input files play the same role as the .NET file or manually entering it, but they can be constructed ahead of time once you understand the file structure. The file structure is described in great detail in the user manual. And I should do the smart mark that nobody ever reads until they have to. So let's return to our problem here. So in this case, to read an IMP file, we'd use the import tool. So we're going to import a network. We don't want to save our current project. And we need to navigate to where the network is located, and there's the input file right there. Choose that, and it's giving us a chance to select the drawing, and there we go. So we have the same thing that is in the PowerPoint presentation, and it's already built. So we'll just pick pipe number 10, for instance. So what had happened there is the analyst had taken the tabular value, drawn the network, and then gone back and entered the required length, diameter, roughness coefficient. In this case, they're using a 1 instead of 0.26. And they entered the pump curve 1, and over here in curve is the pump curve. And you can see the equivalent equation for the 3-point curve. And then the pool elevation of this reservoir, 155 feet. Entered right there. And we can now run the simulation and see what happens. We are successful, which is always happy. And we have it showing nodes in flow, but all it's doing it is in colors, which isn't necessarily very useful. So we can go ahead and go to Options, Notation, and instruct it to display the values. And the flow rate from the pump is 11 cubic feet per second. The flow rate coming from the tank is 4.92 cubic feet per second. If we want to find flow directions, we can go back to our Options tab, choose Flow Arrows. I'll choose Filled. And it's hard to see, but the flow is from the tank into the network, and then the flow here is pumped into the network. It's interesting. So let's make a subtle change. So I maintain, in my mind, it makes more sense for the reservoir to connect to a node and then to the pump. So I'll put a node in. This will illustrate the power of the graphical user interface. It's designed so that it's easy to change a network layout. Actually, can't do that yet. I need to junction 13. So now I go to my pump, and I'm going to start at junction 13. And so now the pump is connected to this node. Next thing I'm going to do is I'll connect the reservoir to that node. And then we'll go back and adjust elevations. And actually probably pipe properties. So we'll make this a pretty big pipe. Get my roughness down to 1, so that should be consistent with the rest of the network. Our pump is fine, and now we have to decide what elevation we want things. We certainly don't want it at 0 because that's a node that's down in a hole. I'm picking 155. That's the elevation of junction 5. And we will keep the pump at the same elevation. So this is drawing water at 155 feet into a node of elevation 155. That doesn't make sense. The water has to be, it doesn't really have to be higher than node, but normally you would draw water from a lower elevation in the reservoir. I'll leave it be, it should run. Rerun the model, and now we have, the purpose of doing that is, to me, this configuration makes much more hydraulic sense. Tank to node, node to pump, pump to node, and then into the system. Especially since this node right there, well, it does not have a demand. I was mistaken. I thought there was a non-zero demand at that point. So this would be how I would construct one of these networks. And that is EPANET, including pumps. Oh, yeah, we went to the pump curve. I showed you that. And so we ran the simulation. Again, we can generate a status report. If we're interested in low pressures, we can try to find the low pressure node by looking at things. In this case, our low pressure node is the suction side of the pump, and that wouldn't be of much concern. The lowest pressure node in the network looks like it's this one here. Alternatively, we can generate a full report and then go examine the report. And from that examination, we can identify the low pressure node in the network, not these two, because these two are ones that we created for keeping the pipe in place, is node number 4, 55 psi. So next time, what we'll do in EPANET modeling on Tuesday is we'll go ahead and we're going to go into extended period simulation. So it'll be the third and the final installment of EPANET for this class. So we've already seen flow equalization. You know how to do that. We're going to examine the difference between tanks and reservoirs and how they're manifest. And then we'll look at how to do that. And we may take next time as somewhat of a workshop and get started building the network for the subdivision that we're studying. And by then I should have another homework assignment prepared and posted. And sometime next week I will program into Blackboard a short examination, like one of the 3 exams for the class. I hope I do a good job and make it easy for you because it doesn't need to be hard. And it's just to keep your mind thinking. So we're going to finish up with that, and we'll probably be done with hydraulic networks for pressurized systems next week. And then we'll move on to drainage. So if there are no specific questions, I will go ahead and stop the recording and end the meeting. You have a few seconds as I do all that shutting things down. Or you can just leave on your own, and that's just fine. So I gotta remember to shut this down correctly. Because if I don't exit this clean, I really can't expect you guys to use it to exit it clean. Okay, so that's a clean exit there. And okay, so I'm going to go ahead and terminate the call. Thank you very much for your attention. Have a great afternoon. And looks like the weather's kind of nice out. It's been cooler lately. I hope you have a chance to enjoy a little bit of it sometime today. Be safe. Don't get infected. Don't infect other people. And someday this will all be over and we'll go back to ordinary classes. So let me see how to get control. And then must be up here. God, I've used this enough, you'd think I'd know how still, but. All right, goodbye, everyone.